So this video will go over section 2 of chapter 10, and that's nuclear reactions. So we'll learn about radioactive decay. So the reactions of radioactive decay are the process by which an unstable radioactive nucleus emits radiation. So we can write a nuclear equation for this process, and it will look like first you have the original nucleus on the left, then the arrow, and on the right of the arrow you have the new nucleus and the radiation emitted. And so the following must be equal on both sides of a nuclear equation. We used to balance the number of elements on both sides, but these are balanced differently. The sum of the mass numbers must be equal. So the A's should be equal on both sides of the equal sign, and the sum of the atomic numbers should be equal. So the number of protons on both sides should be equal. So let's look at examples. First, we'll learn about the alpha emission, which is a decay of a nucleus by emitting an alpha particle, like the name says. So let's look at the example. Uranium 238 on the left. So we see its big nucleus with 92 protons. Uranium is the atomic number 92, so 92 protons, and 238 minus 92 is 146. So we know there is 146 neutrons in the uranium 238. So we know it goes through an alpha decay, and alpha decay means you have an alpha particle being produced. And so you know how we write it as helium, a mass number 4, and 2 neutrons. So 2 protons. So mass number 4, atomic number 2. So that means it's 2 protons and 2 neutrons, because 2 plus 2 is 4 for the mass number. And so when you remove this helium nucleus from the uranium 238, so you need to do 238 minus 4 to get the mass number for the new element. So 238 minus 4 is 234. So the mass number of the new element will be 234. And to get the atomic number, you do 92 minus 2, and it's 90. So the new element has an atomic number of 90. And if you look at the periodic table, that is thorium. So thorium is the atomic number 90. So that's why it's the symbol thorium with the atomic number 90, and the mass number is 234, because it's the sum of 90 plus 144 neutrons. So that's how we get the number of neutrons, by doing the mass number minus the atomic number. And so we see that on the left we had 92 protons in uranium 238, and we have 2 protons in the alpha particle plus 90 protons in the thorium, and that's 92 as well on the right. And on the left we had 146 neutrons in the uranium 238, and on the right we have 2 neutrons plus 144 neutrons, that's 146 neutrons on the right side. So you see how the mass numbers are equal on both sides of the arrow, and the atomic numbers are equal on both sides of the arrows. So this is how we balance this type of nuclear reaction or alpha decay here in this particular example. Let's look at an example of a beta emission. A beta emission is the decay of a nucleus by emitting a beta particle. So let's look at the example of carbon-14. So you know how carbon-14 is used to date archaeological samples, because it decays into a beta particle. Remember how a beta particle is high energy electron. So the symbol is E, mass number 0, charge -1. And so let's calculate the new element. So carbon is atomic number 6. And so 6, so on the right side, we want 6, a total of 6. So if we have -1, we need to add 1 to the new element, an atomic number. So that should be 7, because 7 minus 1 is going to be equal to 6. So the new element will be atomic number 7, and that's why it's nitrogen here. It's the atomic number 7. The mass numbers should be equal as well on both sides of the arrow. So we had a mass number of 14 on carbon 14. Because the beta particle is a high energy electron with no mass number, then the 14 goes to the new element, the nitrogen. So it's a nitrogen 14. And we see how the number of mass number is the same. So 14 on the left, 0 plus 14 on the right. And the atomic numbers are the same on both sides, 6 on the left and 7 minus 1 is also 6 on the right. So that's how we balance this type of beta decay. You can see how overall the nucleus of the carbon 14 has lost a neutron and has gotten a new proton. Overall, that's what a beta emission comes to. Change of a neutron into a proton. Now let's look at the positron emission. So the positron emission is the decay of a nucleus by emitting a positron, a beta plus particle. So remember how a positron is a positive electron. So the symbol is E with a mass number of 0 and a +1 charge. So if we take this time carbon 11, carbon 11 is an element that is artificially made to do some, actually the positron emission tomography. So it is used in PET, position emission tomography. So carbon 11 is artificially made and it's radioactive. It will emit a positron. So the mass number of the positron is 0. So that means the mass number for the new element is still 11, like carbon 11. But the atomic number, we need to remove 1 because the positron has a +1 charge. So the new element should be only 5 because 5 plus 1 will be 6, like the carbon 11. So that's atomic number 5 for the new element. And if you look at the periodic table, the atomic number 5 is boron. So that's why it's B for boron. So the new element is boron. That's how carbon 11 decays to boron 11 by loss of a beta particle, beta plus particle, sorry, a positron. And a positron emission comes down to changing a proton into a neutron. You see how there is 1 less proton and 1 more proton, because you see how the number of neutrons needs to increase for boron to keep the same mass number, because we have 1 less proton, so we need 1 more neutron. And so you see how mass numbers are the same on both sides, 11 and 11, and then 6 protons on the left and 5 plus 1, 6 on the right. So the atomic numbers are the same on the left and on the right of the arrow. So 1 proton is lost, 1 neutron is gained. So let's do let's go over an example to see how we should balance an equation for a nuclear reaction. So we will use the example of americium 241, and we want to write the balanced nuclear equation showing how americium 241 decays to form an alpha particle. So you are told what is the decay, what is the radiation, and it's an alpha particle. So the first step will be to write an incomplete equation with the original nucleus on the left and then the particle emitted on the right. So here, americium-241, americium has an atomic number of 95, so you would put AM is the symbol for americium, 95 is its atomic number, 241 is the mass number. And you draw the arrow, and then we know it's an alpha particle, and an alpha particle is represented by the element helium or the nucleus of helium with 2 neutrons and 2 protons. So mass number 4, atomic number 2. So that's the first step. That's extracted from the text of the problem. The second step is to calculate the mass number and atomic number of the newly formed nucleus on the right. So for this, we will do here, we will do 241 minus 4 to get the mass number. So 241 minus 4 is 237. So that's the new mass number. And then for the atomic number, you do 95 minus 2, and it's 93. So the new element will have an atomic number of 93, right? So mass number 241 minus 4 is 237, and the new atomic number is 95 minus 2 is 93. So we look at the periodic table and search for atomic number 93, and that is neptunium. So that's how we use the atomic number to identify the new nucleus and complete the equation. And so that's why here we can write the symbol for neptunium, which is Np. And so that's how americium decays into neptunium and an alpha particle. So let's do some learning checks. So these learning checks are for you to practice. That means I expect you to pause the video before you watch the solution. So let's read the text. Radon, a radioactive gas formed in the soil, can cause lung cancers when inhaled at high temperature, in high concentrations for a long period of time. Write the balanced nuclear equation for the decay of radon-222, which emits an alpha particle. All right, so the first step is to write. So again, try before you listen to the answer now. So the first step is to write the original nucleus. So radon has a symbol of Rn. The atomic number is 86. We get that from the periodic table. So we'll have Rn 86 on the bottom, 222 for the mass number. It decays, and we are told it decays by emitting an alpha particle, and an alpha particle is symbolized by the helium nucleus with a mass number of 4 and an atomic number of 2. That's the alpha particle. So now we need to find out the mass number and the atomic number of the new element. So for this, we do 222 minus 4, and that will be 218. So that's the new mass number. And for the atomic number, you do 86 minus 2, and that's 84. So you know you need 84 for the atomic number. So this way, we know now the new element has an atomic number of 84. So you look in the periodic table for the atomic number 84, and that's polonium. So the new element will be polonium with atomic number 84 and mass number 218, because the sum of the mass numbers should be equal on the left and on the right. So 4 plus 218 is equal to 222. That's what we have on the left. And 84 plus 2 is 86, and that's what we have on the left. So we know this is the correct new nucleus. Let's try a new learning check. Again, you want to pause the video to try this on your own before you watch the answer. Write a balanced nuclear equation for the beta emission of phosphorus 32, a radioisotope used to treat leukemia and other blood disorders. So the first step is to write the original nucleus, and here it's phosphorus symbol P. Look at the periodic table for its atomic number, and it's 15. So 15 P, and then 32 for the mass number. You are told it's decaying into a beta emission. So beta, remember beta, how it is the high energy electron. So the symbol is E with a mass number of 0 and a -1 charge. That's the beta particle, a high energy electron. So to find the new nucleus, we see that the mass number for the beta particle is 0. So the mass number will be 32 for the new nucleus. For the atomic number, we have -1 on the right. So that means we need one more for the atomic number for the new element, so that -1 will make it 15. So that means it's 16. To get 15 on the left and 15 on the right, you do 16 minus 1. So the new element will be the atomic number 16. And if you look at the periodic table, that's sulfur. So it's going to be S with 16 on the bottom and 32 on the top. Mass number 32 and atomic number 16. And we see that we have the sum of mass number 32 plus 0 equals 32, like on the left. And the sum of the atomic numbers, 16 minus 1 is 15, which is the same on the left. So that's the correct new nucleus. Let's try a third example. Again, pause the video before you watch the answer to practice, and make sure you know how to do this on your own. So write a balanced nuclear equation for the positron emission of fluorine-18, a radioisotope used for imaging in PET scans. So positron emission tomography is also using fluorine-18, not just carbon-11. So let's write the original nucleus. Fluorine is symbol F. The atomic number for fluorine is 9. So 9 at the bottom, 18 on top, because that's the mass number that is given, and capital F. We are told it's a positron emission, so positron decay. Positron is a positive electron. It's an electron, but with a positive charge. So E with a mass number 0 and a +1 charge. So it's a beta plus particle. Beta plus because it's a opposite charge compared to beta. All right, so we need to find the mass number, and because the beta plus particle has a mass number of 0, so the mass number will be 18 on the new nucleus. For the atomic number, we need to remove 1 from 9 because we have 1 from the positron. So it's going to be 8. 1 plus 8 is going to be 9, like on the left. So that means the new nucleus has an atomic number of 8. And if we look at the periodic table, that's oxygen with atomic number 8. So it's going to be an oxygen with atomic number 8 and mass number 18. And we can see that 18 plus 0 is 18. So the mass numbers are equals on both sides. And 8 plus 1 is 9. The atomic numbers are the same on both sides. All right. Let's look at a gamma emission now. Remember how the gamma emission is the decay of a nucleus by emitting a gamma radiation. And remember how gamma rays are a form of energy only. They have no mass and no charge. So that's why it's just the symbol gamma. So their emission causes no change in the atomic number or the mass number. So it is the same element, but with less energy. For example, technetium-99 is a metastable isotope. So the M after the 99 stands for metastable. So it decays by gamma emission to the more stable but still radioactive technetium-99. So it's the same element with the same mass number, same atomic number, but the technetium-99M is higher in energy, and it will decay by giving away gamma rays, which are high energy rays. And so now we have technetium-99, which is still radioactive. So this is used in medical imaging because it emits high energy gamma rays, but decays in a short period of time. So it's used to image the brain, thyroid, lungs, liver, skeleton, and many other organs. So gamma rays often are accompanying alpha or beta emissions. They are rarely on their own. So more commonly, they accompany alpha or beta emissions. For example, cobalt-60 decays with both beta and gamma emissions because a beta particle is formed. It's a different element this time, right? So here, cobalt-60, so atomic number of 27, because it decays into a beta particle, which is a high energy electron with a mass number of 0 and a charge of -1. So we need to add 1 to the atomic number of the new element. And so 27 plus 1 is 28. So the new element is 28, atomic number 28, and that's nickel, according to the periodic table. So cobalt changes into nickel-60 and a beta particle, which is a high energy electron, and a gamma rays. So there are both beta particles and gamma rays that are emitted during this decay of cobalt-60. Cobalt-60 is used in external radiation treatment for cancer. Radiation generated by cobalt-60 decay is focused on a specific site in the body that contains cancerous cells. And by directing the radiation on the tumor, damage to the surrounding healthy tissue is minimized. So see how it is balanced again, because the beta particle has no mass number, the mass numbers are the same. And the atomic numbers, they add up to 27 on both sides. So to summarize here, this is a table that shows the different types of nuclear reactions or decays. We have the alpha emission. So the original nucleus has an atomic number of Z and a mass number A. And so when you have an alpha emission, which is the helium nucleus with mass number 4 and atomic number 2. Then the new element, the new nucleus, will have an atomic number of Z minus 2 and mass number of A minus 4. In the case of the beta emission, we get a high energy electron with a -1 charge and no mass number. So the new nucleus will have the same mass number, A, but the atomic number will become Z plus 1. In a positron emission, the positive electron is emitted, so it's no mass number, but a positive charge. So the mass number stays the same from the original nucleus to the new nucleus, it's still A. But the atomic number changes from Z to Z minus 1 to take into account the positron emission. And in the gamma emission, because gamma rays are only high energy, rays, the nucleus stays the same, the element stays the same, atomic number is the same, mass number is the same. So that summarizes here section 2 of chapter 10.